Okay, looks like we're ready to start with the seventh the seventh video lecture in the conceptual null hypothesis module A series here. So this is hypothesis testing with simulations. Now, to be honest, there's no quiz on this because I don't need you to know the details of this, but I hope you will watch it and think about it because we're going to do stuff like this in class, and I think this really helps you understand what's going on with hypothesis testing. So first things first, you don't need to know how to do what I'm going to do in R, the software. You might ask to be follow along on your, you might be asked to follow along on your laptop or a lab computer in class if we ever make it into a computer lab. But you should try your hardest to understand what's being done because that is the entire point here. The whole reason we do simulations is so we can understand what a p-value is and some other things. So let's do some of the situations that we did before, but using simulation in the software program R. So let's say your friend says he can predict the future. Now let's modify the situation. Let's say you toss a coin 10 times and he correctly guesses 8 times. What are the null and alternative hypotheses? Pretty standard. If this doesn't make sense to you, you should go back and review previous lectures. What's the p-value question? Well, if you can really not predict the future, if the null hypothesis is true then, what is the probability that he would get 8 guesses or more correct out of 10 coin tosses? 8, 9, or 10 out of 10. So it has to be 8 or more, extremely unlikely. So we can we figure out a p-value or something close to what the p-value would be using a computer simulation? Now, in reality, we use this a lot in statistics when we can't really work out the formal theoretical probabilities easily. We just simulate a whole bunch of times and say how many times it happened this way. So we can simulate coin tosses using software easily, but let's just skip past that and simulate Fred's guesses. Fred's guessing accuracy should be 50% on any given coin toss. So the probability of the data or more extreme given the null hypothesis is 8, 9, or 10 guesses correct out of 10. So each guess, he has a 50-50 chance of being right. We can simulate this in software. It's not very difficult once you know how to use some of the commands. But we always have to start assuming the null hypothesis. Hypothesis testing starts from the position that the null hypothesis is true. Remember, innocent until proven guilty. So you look at the world as if nothing were happening that's out of the ordinary. You have to say, what's the null hypothesis? Let's simulate the world of the null hypothesis. So let's simulate lots of ways that 10 random guesses could happen for 10 coin tosses. And we use R. Now, if you have R, crank it up, follow along, but it is not required. I'm going to start R here. This is what R looks like after you double-click the little blue thingy. I'm going to make the font size a little larger here. Let's make it 14 so that you can read the text even if your video is a small video. I don't want this too huge. So I've started R here, so we'll be using that. So there's a function in R. Everything you do in R is typing some stuff in, and then you see stuff happen, or not if you typed in the wrong thing. There's a lot of typing the wrong thing. There's a function called sample for simulating, drawing random samples of things. Think of this as randomly draw such and such number of things out of a bag holding such and such other things. So if you want to see how this function works, you can always type in $sample, enter into the R window. And then you'll see this as part of the somewhat confusing help page that comes up. And this shows you what the function can do. It says sample, and then you put stuff in parentheses. And everything in parentheses needs some kind of a value, or it will take a default value if there is a default value. So you need to tell it an X. So you're not going to type in X. You're going to type in something that works out to be some things it can choose from. And you're going to type in a number for size. You can type in size equals the number equals 5 or something. In this case, size equals 10. Because 10 coin tosses, 10 guesses. Replace equals false. That's the default. You can change that to true if you want. And prob equals null. We're not going to worry about that. But if you want to change the probabilities of things happening, then we can mess with that. Like if it's not a fair coin and it's not 50-50, instead it's a coin that comes up 25-75 probability, you know, heads versus tails or something. But we're not going to mess with that. So we can ignore that and leave prob equals null. So if we want to simulate sampling coin tosses or sampling guesses about coin tosses, we can sample some zeros and ones. So we can create a little bundle of values. The C function says concatenate combine these things together and make like a list. It doesn't add them or anything, it just makes a list so that the computer can understand, hey, that's a list with two things in it, 0 and 1. So we can sample, and instead of X, we'll type in C01 in the parentheses there. And that will be like sampling a 0 or 1 out of a hat, and we'll draw 10 times, so size will equal 10. So it's like sampling 10 random guesses, 10 zeros and 1s. And a 1 means he was correct, and a 0 means he was not correct. And his guessing is random because he doesn't know, because this is the null hypothesis that says he doesn't know, right? So we're going to sample 10 guesses if he's truly guessing randomly, which is what the null hypothesis says. And so every time we draw a guess, we have to, on the next guess, he needs to be able to get true or false, correct or incorrect, right? So you can't, this replace equals false, that's like saying, no, you can't replace, you're drawing two slips out of a hat. One says true and one says false, or one says correct and one says incorrect. And if you draw one, then that's it. You leave it out of the hat, and then you only draw from what's left. Well, that's silly in this particular case. He needs to be able to be right or wrong on every single draw. So we're going to say replace equals true. It's like saying put those slips back in the hat before you draw every time. So we can type this. We can say sample, randomly sample from these two things 10 times, replacement equals true. So I'm gonna do that in R here. I'm gonna say sample. You can put a space there or not. I don't usually. C 0, 1. You can always put spaces in random places. I have to put that comma there because this is all one thing. This is all, or sorry, this is all one thing. And then comma, the next argument is size equals 10, so draw 10 times. Replace equals true. And it has to be in all capital letters. Oh, there we go. Now if I want to sample again, I can hit the up arrow, which repeats what I just typed, and then hit enter and sample again. Now there's a different number of yeses and nos, correct and incorrect guesses. Well, the first one had a lot of correct guesses, but that hasn't happened so much. That was 9 out of 10. Wow. That was kind of unlikely. Okay, so we don't want to know how many correct guesses Fred would get one time. We know how many correct guesses he might get in like 10,000 alternate universes. If he's randomly guessing, what are the possibilities for random guesses? So we use this thing called the assignment operator. It looks like a left-facing arrow. It basically says put the stuff on the right of this arrow into the stuff on the left. So we type up a name of a new object. There's some rules for what the name can be. We're going to call it trial. Pretty much any word without spaces or stars or commas or whatever can be an object. So we're going to create a new object called trial, and we're going to do less than dash. So everything over here, our sample, so this is going to work out to just be 10 zeros and 1s, right? That will be put into this object called trial. So I'm going to do that here in R. I'm going to do my up arrow again just to see what happened before. I'm going to go to the beginning of the string just because I'm lazy about typing. Ooh, let's type all that stuff again. There we go. Now it looks like nothing happened, but actually the object was created. But in R, you don't see anything often unless you want to see things. So if I want to list all the objects, and I created an object called trial, I want to see the objects I've created, I do ls and then empty parentheses, trial. And if I want to see what's in trial, I just type the name of the object. There we go. Those were the random things, the random values that I created there. So we can find the sum of our guesses, and this is what we want to do every time in every one of these simulated trials. We want to not find a 100101 thing like that. We want to see how many ones there are, because we're thinking to ourselves, the ones are like him being right. So let's just add up everything in trial. The zeros don't count because they're zeros, and you're just adding up the ones, right? So we can do sum of trial. In this case, there were 8 correct guesses. Pretty good. If I do this again, then I calculate trial over, and the old trial gets replaced with a new trial. Now if I look at what's in trial, now it's a different thing. And now if I do sum of trial, we've got 7 this time. Okay. On average, there should be 5, but we got kind of a high number. But if you see up here, sometimes there were low numbers when we randomly did this. But random means random. So nothing really happens, nothing changes in your workspace. You didn't create any objects when you said sum of trial. You just showed yourself. You're just like saying, hey, give me a report. What's in there? So we can assign that result to yet another object, which we can call trial correct. Trial.correct. assign the stuff that's in some trial. So this creates a new object called trial.correct. You can have periods in these objects, and it assigns it to, or it assigns to it the values of the sum of whatever the trial is right now. So if I type in trial.correct, it should say 7. There it is, because I put this value in here, that value in there. And now if I do lists, I've got 2 objects, trial and trial correct, which are actually the same. So we need more than this. We need to do this a lot of times. Let's do this 10,000 times. We need a for loop. Now you don't need to know the syntax of this, but we do use it a lot in simulations. Every computer language has its own little details for how to do a for loop. So first we're going to create a blank container. I'm going to say results are rep. Rep is a function that says repeat this thing this number of times. So if I say rep 100, it gives me 100 ones. And these are just counting the numbers so I can kind of see, but it gives me 100 times. So if I do results and repeat NA, NA is a special code in R that means nothing. It's a blank. 1, 0, 0, 0, 0, 10,000 times. If I want to see all those NAs, I can type results. There we go. There are 10,000 NAs. That's a lot of NAs. That's what we created. Okay. So let's do that, and that's going to hold our values. But you can look here. You could look at the 9,000th NA, or 9,976th NA, and that's what we're going to do. So we're going to create NA, and now we're going to loop. And you don't have to understand this totally, but if you want to type this all in, go ahead. Now what I did, we're going to do this for loop, and the for loop says everything that comes after it will be done this number of times, from 1 to 10,000, do the stuff between these brackets. The brackets mean just do stuff on multiple lines as if it were one thing. So we're going to, 10,000 times, we're going to create an object called trial that is 10 randomly selected ones and zeros. And then we're going to add up the number of ones, and that's going to be the number of correct on that trial. And then this is interesting. The results has 10,000 things. The bracket I after results says the ith thing. So if this is loop, this is the 500th time it goes through the loop, then it'll count through to the 500th thing in I, because results has 10,000 spaces that are all NAs, and it'll replace the NA with whatever this is, with the number of trials that was correct. And if you can't wrap your brain around this right now, don't worry about it. But I'm going to do this here. I think I have a text thing here. Maybe I don't. Anyway, if you run this, and I'll just type this, for I in 1 colon, that's how you do from something to something else, 1 0 0 0 0. And then I'm going to do the open bracket so that, and R will change its prompt to this that says, I'm still waiting for more. You're not done yet. I'm not going to calculate anything. Trial. Oops, that's an error. Sample C01 size. You have to do this just right, or else you get an error. I probably should have just copied and pasted this from Notepad or something. And trial.correct is the sum of all those little ones and zeros in trial. And then results bracket I is trial.correct from this time through. And that's right. And close. Huh. So we typed in results before and we got 10,000 NAs, right? Now let's type in results and see what it is. Now results is the results of 10,000 times, here's where it starts, of 10,000 times that Fred guessed. So we did it. We simulated 10,000 things. So how to make sense out of that? We can calculate a simulated p-value by just looking at how many times if Fred were guessing randomly, he might guess 8 times correct, or 9 times, or 10 times. A frequency table will tell us that. There's a function called table, and that's just a frequency table. It's a really handy function. So results is this 10,000 individual numbers between 0 and 10, right? So table of results. Shows us a frequency table. There we go. So 7 times there was 0. 0 times correct. So he's right a lot of the time. He's right at least a little bit of the time, usually. 87 times out of 10,000, he was right only once. 412, he was right twice. So we're interested in this. How many times was he right? 8, 9, or 10? So in the simulation I did to write this, this PowerPoint slide, this is what I came up with. This was my table of results. So here it is again. And so if we add the number of 8s, the number of 9s, and the number of 10s together, then we get the total number of times he would be expected by pure random chance to guess 8, 9, or 10 times right out of 10,000. But it's out of 10,000, so we need to divide. So we need to divide 573, which is these 3 things added together, by the number of times we simulated. So about 5.7% probability. Now, over here in the simulation, we've got something different, because every time you run random, it's slightly different. So what is 452 plus 96, our makes a great calculator, plus 7. So and then what's 555 divided by 10,000? 0.0555. So it's 5.6%. So in this one simulation, we got 5.7. A current simulation here, we got 5.6%. So this is really zooming in on things. The simulated probability is 5.057. The true probability, the true theoretical probability is 0.055, actually, which is incredibly close to what we got here. This was slightly higher at 0.056. So our simulation worked. We just said, hey, computer, 10,000 times simulate Fred guessing, and then show me how many times he got 8, 9, or 10 correct. So is he clairvoyant? These results would have happened about 1 in 20 chance by pure chance. So how could you get a better idea of whether he has high coin guessing powers? That's just an interesting thought experiment. How could you set something up to really test this more rigorously and be more sure? Because 1 in 20, maybe you're not comfortable saying he's really clairvoyant there. So I messed with the poker example, and the poker example here is changed, so we only want to know the probability of getting 2 poker hands in a row that have 3 of a kind in each hand, just dealt randomly from the deck. Because as it turns out, 4 hands in a row, even 3 hands in a row, was so crazy unlikely, I had to simulate like 100 million times to make sure it even happened. And that takes a really long time on your computer. So she gets 3 in a row, or 3 of a kind, a triple in 2 hands in a row. The null hypothesis is that she's just lucky, so that's what we're going to simulate. The p-value question is if she's just lucky, if it's random what she's getting and she's not cheating, then what's the probability that she would be dealt a triple twice in a row in 2 hands there? So we can figure that out with a simulation. We simulate, and I used 50,000 games this time, which would take 10 to 15 seconds for this computer to run. 50,000 games, and each game, Alice gets dealt 2 hands, and we count the number of games where in 2 hands she got 2 triples. Now, if you can't follow all of this, that's fine. But if you can, it will be helpful when we start using R in class from time to time. So we can make an object in R that is all the card face values. So we can do this business here. And I actually have a text file that I copied and pasted this stuff from. So I'm going to paste this into R. The card values is this. So if I type in card vals now, I've got 1, 2, 3, 4, and these are text values. The 1 is not actually the number 1 as far as R is concerned. It's just a letter that happens to look like a 1. And we have to do that because within the C parentheses thing, they all have to either be all numbers or all text. So since we wanted J, Q, K, I did all text. And then we can do use this function rep, which says that repeat the card values, that whole list, repeat it 4 times, and put that together and make that this object called cards. So looking back at R, I type that out elsewhere. And you'll notice that it has this hash sign, this number sign. Everything after that can be just like a comment to ourselves, because R will ignore it. It won't try and calculate it, won't give you a syntax error. So now if I look at cards, here we go. Oh, how handy my screen is just wide enough. There are 52 values here. So there's 1 through K, 1 through K, 1 through K, 1 through K. So length of cards, length is a function. It tells you how long something is, how many things. There are 52 cards. Okay. Now we can sample from that object. So if you do sample cards, it will give you a lot of things. So if you do sample cards size equals 1, that's like drawing 1 card. If you do sample card size equals 5, and let's do replace equals false, because being dealt a deck of a hand of cards, if you get dealt the queen of spades, you can't get the queen of spades again in that same hand, right? You can get the queen of clubs, but not spades. So I got a 7, a 4, an 8, a 9, and a 7. I hit my up arrow again to get my last command and enter here. So you can see this is like dealing yourself random cards. You could write a really weird poker simulator with your friends in R, like doing this. You could each give each other hands. So I'm going to assign that to an object called hand. And if I type hand, I can see what the hand was. I kind of fixed that in time now, that one hand. Oh, an ace, a 10, an 8, a 4, and a 3. We don't know what the suit of those things is, but for this simulation, it doesn't matter. All we care for triples is whether the face value is the same, not the suit. So now we can check to see whether at least 3 cards in a hand have the same face value. We can use that frequency table, table hand. There's a 1, a 10, a 3, and a 4, and an 8, and none of them recurs more than once. So they're all, if you had 4 and this said 3, that would mean there were 3 4s. So we can piggyback on that, and we can say a triple is any of these values in the frequency table greater than or equal to 3. So we can do that. So we can say, let me just paste that here. If you're following along, you can follow along. So a triple is just going to be what we call a Boolean. It's just a yes or no, a true or false. False. In this hand, there is no triple. So we can use that to build our simulation. So let's try to let's do 50,000 values. Slower computers might take a long time. Mine seems to take about 10 to 15 seconds, I think. Remember that Alice gets 2 hands of cards for each trial. We have to calculate 2 hands every time and then combine the results there somehow. So if you can't follow this, go ahead. But if you can, we're going to do this thing where we create, oops, I'm going to fix this in my R. This is going to be 50,000 times, not 10,000 times. But this is, I'm going to change this to 50,000. I'm going to create a results object that has 50,000 blanks, 50,000 NAs in it. So results. If you want to see them all, woohoo, results. There, 50,000 NAs. It's probably not even going to show us the beginning. Oh, it did. It showed us all 50,000. Holy cow. Yeah. And more. So it's a lot. And then what I'm going to be doing here is I'm going to create an object called hand A. That is this thing that we did that samples 1 hand. And then triple A, which is going to be a true or false. Is there a triple in hand A? Hand B, which is sampling some cards for 1 hand. And triple B, was there any triple in triple B? Then I'm going to create a new number of triples, a num.triples object, and it's just the sum of triple A, triple B. Now triple A is just going to be a true or false. Triple B is going to be a true or false. But R, like many computers, treats true or false like numbers. A true is like a 1, and a false is like a 0. So if you sum things that are true and false, you'll get a 0, a 1, or a true, because it'll be a 0 and 0, or 0 and 1, or 1 and 1. And then the results, remember there are 50,000 of these, or 10,000, whatever. I'm going to have 50,000. Whatever number of results we are on the loop through, I'm just going to put the number of triples there. So this is going to give us, you'll see, 50,000 values. So I'm going to paste that sucker in. I'm going to paste these values and hit enter, and we have about 10 or 15 seconds to wait. See my cursor twitching and spinning there. It's calculating. It's doing this 50,000 times. It's a pretty quick computer. If you have a slow computer or laptop, you might not want to run 50,000, do maybe 10,000. All right, it's done. So I can look at results if I want to now, but it'll be 50,000 things. Look, it's all zeros, ones, and twos. Well, that's the previous thing we typed. Here we go. This is where we started. So to see what's going on with those results, I do a table of the results. Table results. So way most of the time there were no triples. Sometimes there was a triple, and 30 times there were 2 triples in 2 hands. So that's the results here. So in the simulation I did before, I had 35 times out of 50,000, and that gave me a ratio of 0.0007 times out of 50,000, or times out of 1. There was 2 triples in a row. So 7 chances in 10,000, less than 1/10 of 1% probability that Alice would get, that she would get 2 triples randomly dealt to her in a row. Now let's go back to this simulation. We have 30, so 30 divided by 50,000 is 6E04, so 6 times 10 to the negative 4, so it's 0.0006. A little bit lower here, so 6 chances in 10,000 instead of 7. Very close. So our simulation, the theoretical probability should be, according to this website I found, 0.021 times 0.021, which is 0.00044. Now, 2 simulations of 50,000 each, I found something higher. It was 0.0007 and 0.0006. So maybe the website's wrong, or maybe my simulation was off in some way. Something to think about. Either way, it's in the ballpark. It's pretty close. So once again, it was reasonably accurate. So 7 times in 10,000. Do you think Alice cheated? Now, when we simulate something extremely rare, we have to use big numbers. So tiny random fluctuations of those rare things don't mess up our data. Like I said, 3 and 4 hands, you have to use simulations of 100 million or something like that, 10 million, to make sure that you get enough times that the 3 and the 4 hands happen that you can get a p-value. This is a problem with extremely low p-values. Anyway, we're going to end this right here after a recap. To simulate, you come up with a hypothesis testing situation, you formulate what the null hypothesis is, and you observe the results of your study, and then you simulate the most probable random outcome if the null hypothesis is true a whole bunch of times, and then you count the number of times that the simulated results happen, and say how unlikely is it that our results would happen? What proportion of the simulated results are as unlikely as the observed data that we found, or more unlikely? So you just count the number of times your data or something more extreme happened in your simulated results, and you turn that into a percentage or proportion, and that's your p-value. That's your simulated p-value, and it tends to be pretty accurate if you specify things correctly. The end.